delta G0 is Gibbs free energy, and that is related to delta G0, and that is directly related to equilibrium constant, and all others are kinetics. Kinetics, reaction rate, same meaning, and that is determined by activation barrier. Okay. So with a double dagger, okay. Delta 0 is a state energy, double dagger is for the activation barrier to the tension state. Okay. Okay, so this is related to directly related to reaction rate, energy state, delta G0, equilibrium constant. We just said that terms we call thermodynamics. That's a state energy comparison. And in comparison to thermodynamics, this one, what do you call? Thermodynamics, the other one? Energy state, status state determines the equilibrium constant, that's thermodynamics. And reaction speed, what do you call? Kinetics. Kinetics. Yay! Oops. So that's a kinetics. Okay. Kinetics is for, this is the basic two terms for all thermodynamic theories. Thermodynamics is for the state. Kinetics is for the speed. Okay. You will hear this all the time. Kinetics and thermodynamics. Okay. Now we are learning the alkene. Alkene is sp2 carbon. 또 다음이야. 1, 2, 3, 4, 5, 6. Okay? Including this atom, everything is on the same plane. 6 atoms at least. Pi electrons dissolved in 2. Okay, again, the pi bond, the pi electrons are neutrophile. Okay, as a general term, H plus is acid. Acid is a part of an electrophile. Okay. Neutrophile can combine, contains base. Base is also nucleophile. Bigger term, nucleophile prefers positive charges. Opposite. Nucleophile prefers positive charges. Electrophile prefers the negative charges. Okay. This is the last chance to summarize the isomers. Constitutional isomer is defined by structural isomer connections. Okay, structural isomer, constitutional isomer is the same meaning, and then all others can be stereoisomers. Connectivity is the same, the spatial position is different. Cis and trans is stereoisomer, specifically not enantiomer, that's the diastereomer. Okay, enantiomer is a mirror image. And conformation enantiomer is defined by rotations or changes of the structures. Connection is not changing. That's kind of stereoisomer too, but at room temperature they keep changing to each other. That's conformation enantiomer. Okay. This is carbocation, transition state, starting material, product. Okay. Okay, carbocation has a sp2 structure. Carboanion, sp3 radical, sp2.5. That's in between. sp3 and sp2 is slightly bendy. Okay. Okay, based on this, we move to alkene structures. Okay, this. Okay, today we study about alkene. And it contains some reactions. All the reactions are alkene as a nucleophile. Okay, alkene plus HCl by alkene plus HBr. That reaction we are going to learn. Okay, if you break down the alkane, like a long hydrocarbon, if it breaks down in the middle, okay, by giving hot energy. So very high temperature, very high, right? 900 degrees. Very high temperature, it can break up. If the alkene breaks up, surface area is increased or decreased? Is it increased? Surface area, if you break down one big chunk, surface area increase, decrease? Increase, right? If the surface area is increased, required hydrogen number is increased or decreased? That's also increased, right? But if you don't supply more hydrogen, if you break down, it needs more hydrogen, but there is no hydrogen, then what happens? It forms alkenes. Okay, sometimes it forms hydrogen too, but if you keep going, maybe this hydrogen can be inserted somewhere. Okay, the lack of hydrogen number may induce this double bond formation. We can think maybe the reaction happens if you break down starting from the butane. If you break down, you can break here, any positions. It's randomly vibrating. Heating and heating, if it goes over the activation barrier, it breaks. Homolytic or heterolytic? Homolytic, right? That's why it generates radicals. So it generates breakdown here. So half head, okay? If break down here, it may generate this kind of a radical. And if there is only two components like this, one option is generating one hydrogen and then two alkenes. Or maybe one alkene and one alkene is also possible options, right? So anyway, if you break down the big alkene, then partially it may form alkenes because the required hydrogen number is increased, but there is no hydrogen. That's why to accommodate this situation, double bond is generated. So in this theory, alkene can form under this rate. And then related the topic we already studied last week, degree of unsaturation. By giving the formula, you can calculate how many double bonded character there, right? So either double bonded character or ring character number together. That's what we call degree of unsaturation. That's what I'm not going to repeat today. So I can name it. This compound, do you agree with this naming? Longest chain of this molecule? Should it be pentane? It's alkene, so everything is saturated. We call them alkane, pentane, right? Now, if it is a double bond included, we call in, alkene. But we don't call this as going this way. This is the longest number is 6, and this can be hexane. But we call pentane. You can guess what's the rule here. If there's a double bond there, we count those longest carbon, including the double bond. If it goes this way, we can call this alkane, but we don't count that as main chain. If there's any double bond, triple bond, we use that, including that double bond as a main chain. Okay? That's why we go this way. So, pentane. Okay? Ethyl pentane. And we need to give the number. Right? So, same thing, the numbering. Now, by giving this carbon number 6, so hexene, and point. Of course, you start with a lower number from here, 1, 2, this way, not this way. And then starting point, this alkene is the point of this. Okay? If the double bond is here, that will be 1 hexene. Now this is starting from the carbon 2, that's why we call this 2 hexene. Make sense? 2 hexene. Now substituents. Carbon. Alkene number wise, it can go this way or this way, same. It's in the middle, right? It's anyway, it's a 3 hexene. Now substituents, you want to have lower number. Okay? So starting from here, 1, 2. 2 methyl, 3 hexene. Okay? Now this. Going this way, pentene, and then 1 pentene. Right? Now here, counting this one first, 2 ethyl, 1 pentene. Means substituents first, and then alkene position. Okay? 2 methyl, 1 pentene. Let's look at this. Now 2 in, and 1, 2, 3, 4, or 1, 2, 3, 4. Ordering to give this lower number, if you go from here, that should be 3 position. So we use this one. 2 methyl, 1, 2, 3, 4, 18. But 2 in. So we call di-in. Okay, position, 1 position starting here, 3 position starting here. 1, 3 dibutene. 2 ethyl, 1, 3 dibutene. 그냥 들으면 그럴 것 같지. 막상 써보면 쉽지 않을 거야. I promise in the next week, the exam, I put up some giving name problems. That means you need to practice. This may be the last chance you practice until next Tuesday. Okay? Try to write down the name of each compound. We learned so far alkane, cycloalkane, and stereochemistry, giving ALES, okay? And then alkane. We didn't learn much. So this is the perfect chance you summarize those knowledges by practice. Okay, now, originally we used these terms, butadiene, to make it a little more systematic. Now, new system, we use this one, this is the older system. 3 heptene, now, hept 3 in. To make it a little more systematic, moved this 3 inside before this in. So all others in the beginning, those are substituents, dimethyl, okay? And then where is the alkene position? So this is giving you the number of the carbon, and then this is the position of the in. Basically it's the same thing, but it is a suggested. This is maybe a little more systematic. Now if you look at here, so 1, 2, 3 in, and then 2 position, 5 position, 2, 5 dimethyl, and 1, 2, 3, 4, 5, 6, 7 peptide. So 2, 4 dimethyl, hect, total number of carbon, and 3. Or older system wise, 2, 5 dimethyl, 3, and peptide. As you can understand, so far still we use both. But this is recommended as a new form. You can write any of them. Okay? Now here, 2 in, carbon number 6, hexene and hex 1, 4 diene. Okay? 1 position and 4 position. Hex 1, 4 diene. Now substitution, so propyl here, 1, 2, 3 position. 3 propyl, hex 1, 4 diene, or 1, 4 hexadiene. Okay. Only this numbering was given either inside here or outside here. Either one is fine so far. Okay, this is the naming of open chain alkane. Cycloalkanes. Now this one. If there is no double bond here, that's a cyclohexane. And we can call it cyclohexene. Okay, and 1 position methyl group is added. So 1 methyl cyclohexane. Is that enough? Why don't you call this 2 methyl cyclohexane? If you count from here, 1, 2, 3, this direction, right? Or why don't you call 2 methyl cyclohexane? Lower. 1 is lower. That means if it's open form, you go from one direction to the other. The cyclic form, you can go this way or this way. Right? So that means starting from one alkene, you include this and then move this way, or starting here, move this way. Okay? And the position, you choose the lower number. But my question is that enough? You don't need to define 1E. The systematic name suggested adding here 1 methyl cyclohex 1E. Okay? You don't need it? That's obvious using this structure. In this case, it was not obvious. With this numbering of substituents, 3 position, it does not define that what is the position of double bond. But if it is a ring structure, okay, if it is a ring structure, then the pointing out this position as 1 is obvious, self-obvious. That's why if it's obvious, we don't use it. If it's obvious sister terms we don't need to distinguish, then we don't use it. Okay? So that's why there's a low 1 in here. This one. Now we can go from this position to the other or here to the other. Now it's a symmetric. So saying 1 position, and now we need to give the position of here and here because it can be another option, 3, 4. Okay? That's why it gives 1, 4 the cyclohexadiene or cyclohexa 1, 4 diene. This number in the insert here or outside. Okay, cycle. Now this one, cyclopentene. Position-wise, 1 position, and it cannot go this way. It should go this way because double bond comes first. Okay, so it goes this way. 1, 2, 3, 4, 5. 1, 5 dimethyl cyclopentene. How about going this way? If you start here, it could be 2, 3. 2, 3 dimethyl versus 1, 5 dimethyl. Which would you choose? 1, 1. You should choose the first number. Okay? So this is naming. Of course, if I add more structure here, it can be more complicated and more, the problematic things there. But I will not give you that complicated one. Okay? The rules you learned so far for the alkane, cycloalkane, stereochemistry, and alkane this much. Okay? Practice. Purpose of exam is not totally new. Purpose of exam is to lend you the chance with some pressure. I need need to study and summarize what I have learned so far. That is the main purpose. Okay, don't lose the chance. Okay, this is naming, and a little more naming. It's a very useful information. If it is a double bond and connected directly something, then this one we call vinyl. One more methyl group here, and this is very often we encounter. This is what we call allyl group. This is a vinyl. This is a allyl. If it's connected directly like this, it's not very often you may see, but this is called a methylene. This much is very useful if you encounter any problem and you will see. Maybe you will study this. This is benzene. If it's connected here, have you learned this? What do you call this group? Benzyl. Looks like it can be benzyl, but interestingly, this is benzyl. Okay, this is the benzyl. This is what we call vinyl. Okay. So similar way as the extension of this, if it has a one more methyl, this is similar to benzyl. Property is also very similar. Allyl, benzyl, very similar. Okay. Phenyl, vinyl is similar. Okay. You can put up this structure here in your notebook. That is very convenient or very useful information. Okay. Now, system trends. We talked about it a little. If we have a double bond, before that we already have seen system trends. When did you see? In which case? Ring structure, cyclic structure. Then it can be to the same direction or opposite direction. Same direction we call cis, opposite direction we call trans. Right? Now, here, through double bond, we can see that kind of situation. Now, double bond, pi electrons, we believe they are on the same plane, like this. Pi bond, okay, like this. But if that pi bond is rotating, it's a half rotating like this, then in overlapping of this orbital, okay. So let's look through this angle, then lower blue, upper red. If you have same node like this, if you look through this one has overlapping, this one has overlapping. Now they are more stabilized. If it's opposite, then it's a 90 degree, then this shows like this. In this case, the overlapping, if you look at here, overlapping was doubled in both sides, it's stabilized. If it's the opposite direction, 180 degree, plus minus, plus minus, minus plus, then it's no interaction at all. It's actually replacing. It's unstabilizing. It's anti-bonding. Okay. This is bonding, and this is anti-bonding. More unstabilizing the situation. If it's 90 degree, then overlapping here is negative effect. This is a positive effect. Here positive effect. Here negative effect. Then all cancelled out. If it's exactly 90 degree. Then originally this one bonding, this one anti-bonding, 90 degree. What would you like to call? It's in between bonding and anti-bonding. No bonding. Okay. If it's a 90 degree in English, what do you call? Mathematically. Perpendicular is one way. A little more scientific terms. Orthogonal. Okay. Also means this is the following exact rule kind of things. Okay. Orthogonal means this is a perpendicular mathematically. That means orthogonal, if the chemical bond is orthogonal, that means there is no interaction. Interaction is cancelled out in any directions. Bonding preferred. Anti-bonding unpreferred. That's why it can be pushed out. But no bonding, it doesn't matter. It's there or not. Okay. So if the double bond is rotating up to 90 degrees, there is basically no bonding there. That means maybe one radical here and another radical here independently. That's kind of the situation. Okay? So that energy is almost the breaking energy of the pi bond, about 50 kilocalories, kilocalories more. Okay. So through this bond, you need to give energy to break this bond. That's why in most of the cases, without strong energy, this one and this one is a different molecule. You can isolate them. That's why we need to give the separate name for them. Now you can see here, this one is the same side, cis. Opposite side, trans. If it's a simple molecule, we can say so. But if that is the case, like this, let's think. Through the double bond, one side is different. The other side is the same. If this side is the same, then we cannot define cis or trans. They are same molecule. Okay? Even though B and A is different, but if you rotate it, then that's the same molecule. Now, if A, B, C, D all different, now we know that this molecule and this molecule is not same, but how do you call this? This is cis, which is a cis? If the situation is, if the two of them is the same, then we can say with cis and trans. If all of them are different, then AB, BA, those molecules are different, we can see. But it's difficult to say cis or trans. Right? So in that case, now we introduce another notation similar to RS rather than cis and trans on the ring. Now RS value wise. So we use different term E and G. Through this double bond, you count which one is the higher. If there's a higher one is on opposite side, we call E. E is the German word Entgegen. It's the opposite. Okay, through this is the opposite. G is a zusammen. It's like a together. Okay, that means it's on the same side. Through this double bond is on the same side. Through this double bond is the opposite side Entgegen. So E and G. It's similar to RS. If there's a point parallel to the center, we can define RS values. And RS, we put that into parentheses. Same way, E and G, now from now on, if we need, then we give that notation. Now this priority, how would you give, you think? That's the same as RS. Fortunately, you don't need to learn the new system. We follow RS, the priority system. Means higher atomic number is the higher priority. Exactly the same rule to the RS. Okay, now let's come. Now this. Now, in one sense, we can call methyl group here, methyl group here. We can call cis. That's one system. That's also working. At least we agree that methyl is the same. Then you can call this a cis molecule. Molecule structure-wise, butene, right? And then 2-chlorobutene. And 2 position also you need to give 2-chloro-2-butene. And here, if you give cis, that's also fine. But cis-methyl way, now you compare these two. Proton, hydrogen, and methyl, carbon, hydrogen. Chloro, methyl, chloro and carbon, chloro, hydrogen. So this is the opposite side. Cis sounds like the same side, then you may want to give a G to them together. But this cis-methyl way, the naming wise is different. That's E, it's up. Okay. Previously we have seen RS and DL. In many cases they overlap, but it's not always. RS and DL is a totally independent system. RS you can give by this priority. DL, how do you define? By optical rotation means by experiment. Okay. So it's not always the same. Similar way here, cis and trans and EG is not always the same. Okay. Now here, Same molecule, yeah, same molecule. No, it's the same way. Higher, or the same side, we give this SG. Okay? Exactly the same way, if it's RS, we give R like this. Okay? Same notation. Only when you need to give it. Okay? Now this molecule. Let's think of the priority. Here, which is higher? Carbon, clear. Between these two, which is higher? Upper one, because this is a carbon, and this is also carbon. If the first atom is the same, then you count the second one, right? This is connected to two carbon. This is connected to one oxygen. One oxygen means two carbon means. Higher atomic number, one oxygen means. If it's the same, then you count those number, but if it's higher, then oxygen is higher. Okay? Then higher, E or G? It's G, same side. Okay? So this is G. Okay? As you see, you need to practice. We have a solution book too, right? So by looking at those solution book, by giving those your answer, we don't grade your homework. So you need to check whether you are getting the right answer by looking at the solution book. Okay? Practice. Okay, this is the naming. Now property. Double bond. Now, if you put acid catalyst in between, interestingly, those system trains, they are converting to each other. They are in equilibrium. Mechanism, we'll see that later, but anyway, they are in equilibrium. And which one is more stable? By looking at that value, which one is more stable? So this is more stable. Maybe we can see, in this case, maybe this has maybe some static hindrance between two, push each other, make it a little unstable. Maybe trans may be more stabilized form, we can think. Okay? So two ways to show that which is more stable by giving those percent. This percent gives you what value? Ratio of those two value is what? Equilibrium constant, K, okay? Capital K. That's equilibrium constant. Or if you don't know exactly this number, then still you can draw that with this the arrow. This is a longer arrow, this is a shorter arrow, means this is more preferred. Right? And also this arrow shows that this is equilibrium, not resonance. If it is a resonance, how do you draw? Two head. Okay, single line, two head arrow. That's resonance. Okay, now if you look at this. Now trans and cis to form. To compare this energy level experimentally, one way is to convert this into same product. Okay, actually one simpler way, let's talk later. So here, if you add hydrogen to this, and both of them form same product, correct? Then you can compare those energy level for each reactions. Something like this. Product is the same, so you have the same standard. Okay. Now, if you measure those delta G0, which gives you the status of each molecule, then this is activation barrier up to here, or up to here, up to here. Now, these values can tell you that energy level, if you compare them, you can see which one is more stable, because you have the same reference molecules. Okay. By comparing those, now this delta H is for specific reaction, hydrogenation. Hydrogenation means adding hydrogen. Okay. If you compare those hydrogenation energy, this is released a lot more than this. Right? Cis released more energy than trans. That means which is more stable? Cis generated more energy to go to the same product than trans. which molecule is more energetic? Cis has more energy, that's why it gave more energy, the more released energy. Right? So more energetic means it's more unstable. Okay, trans is more stable. So more energetic, more unstable. Lower the less energetic means it's more stable. By comparing these values, now by looking at those hydrogenation delta H, we can compare those energy level, relative energy level. Now here the comparison is ethylene OH, monosubstrate, disubstrate, cis and trans we just have seen. Trans is a little more stable. But if you compare those, every order reaction is just adding 1 molecule of hydrogenation, it's the same reaction. And then if you compare all of these, then you can see those are trend. What conclusion can you make? More substituted, then less stable or more stable?
More stable.
More stable. Substitution is higher, then it's more stable. I want to say here, they compared this hydrogenation reaction. But if these two are isomer, you have a simpler reactions. They have the same molecular formula. What can be simpler reactions? Just a burning, combustion. Just a burning, and they generate CO2 and H2O. Right? Then that energy level difference will be almost a similar way you can get, just a different standard you use. Right? That could be easier another reaction we can think. But problem is, now if you compare with a different molecular formula molecule, then that's difficult to apply. All the molecules should have exactly the same carbon number, same hydrogen number. Now we know the relativity energy. Energy is what? Einstein said energy is 알잖아. mc squared. This mass, this is atomic material, has very high energy. That means if you have a different molecular formula, their internal energy is very, very high. So it's very difficult to compare to each other. That's why in the textbook they chose this hydrogenation reaction by adding 2 hydrogen to the bracket. Still, those relative energies cannot be exactly the same, but still it's a similar reactions. Then they relatively is acceptable. The energy comparison is possible. Okay. More substituted, they are more stable. That's the conclusion. Tetra substitute is more stable than mono or even no substitute structure. At least for the double bond character. Okay, that's one thing we learned here. And explanation why this is CH2, it has one more CH3 here. Why this molecule is more stable than this? Any good idea? This molecule is isolated pi bond. Say again? Delocalization of
electrons.
which electron? To where?
Pi on electrons.
Pi electrons are delocalized to this method. Do you agree? Yeah, that's a good starting point. Now, if it has a one more methyl group here compared to this, now this 5 electrons. And then here it has a CH3. Actually, it doesn't have a 5 electron. But this CH bond, partially this is CH bond, originally this was a CH3, the sp3 carbon. But if it's oriented, this carbon is on the same plane, if it's oriented to that, then there is a partial sharing effect. It's kind of sharing a little bigger space of the pi electron. Now, whether which electron is donated is not very clear, but explanation is that this sigma bond here, CH, is participating in this pi bond system. It's not really pi bond system, but it's a partially pi bond character is participating, making this small double bond character into a little bigger space. So previously we have seen resonance structure, pi bond with a radical, pi bond with the positive charges, pi bond with the negative charges. All of those cases, resonance was possible. Whether this side gives electron to this system or this electron is given to the other system, it doesn't matter. In any cases, if it has pi bond has more space to be expanded, that's more stabilized. That effect we call, it's a little different but related to conjugation, hyperconjugation. It's good. Okay, that's a kind of interesting concept and also kind of accepted concept now. Why substitute alkene has more stability? By sharing a little more space, now here there is no space to expand it. It's just a confined, small box. If it becomes a bigger box, we learned about resonance, and then later we will learn about conjugation, adding double bond to another double bond, making it even bigger. That's more stabilized. Now this is one carbon position, but it can be partially expanded. Okay, if it has another one, it's getting better and better. So in this case, it has expansion is possible to this way and this way, two ways. This one has only one reaction. That's why it's explaining that this one is more stable than this. In this case, these two are the molecules. Can you use a combustional comparison? By burning and then compare those stability is possible? Or no? Not possible because those two molecules are isomer or not? Those two molecules have the same molecular formula or not? They do. They are isomers. You can do combustion. Burn and then those relative combustion energy comparison is also possible. If they are isomer, composition is the same. Then by burning, the product is the same too. CO2 number, H2O number is the same. Then we can burn and compare. That's also possible. 뭐가 이상했어요? 아이소머가 아니에요? Acceptable? They are isomers. If they are the same composition, then you can do by burn and compare is possible. Okay. Now let's see. Maybe the only reaction you will learn before the midterm exam. Okay. The reaction we already have seen. Double bond plus HCl or HBr. Okay. We have seen this reaction several times. Which is a nucleophile? Alkene.
Yes.
The pi bond, pi electrons, they are electron rich. They can move from that position, attack which one?
Hydrogen.
H plus. Hydrogen, maybe it's better to say maybe proton. Okay, when it's attached to Cl, it is hydrogen, but character will be changed into proton. Okay, because it's a heterolytic breaking. If it's a homolytic breaking, there's a hydrogen radical H. Heterolytically broken, that's a proton. If H has a 2 electron, name? Hydride. Okay, you will see that later too. Okay, in this case, this electron attacks this proton. This electron attacks this proton, and then Br minus is released. And it forms carbocation as an intermediate. Okay, carbocation is intermediate, not transition state. And Br minus plus is the binding together and forms the product. So this is the only reaction you will learn today and until the next class. And this diagram we have seen too. This one and this is delta G, delta double dagger shows activation barrier. Energy state between to delta G0. Thermodynamics kinetics. Okay? Thermodynamics define equilibrium constant. Kinetics define reaction speed, reaction rate. Okay? Now, intermediate is this kind of carbocation, and then this is the product. This is combined together to also be this product. This the diagram you need to be able to draw and explain each energy state. Okay, if you look at specific reaction with this methyl propene and the HCl they added together, H added here first, and then Cl come back and the attack. Similar reactions now. This one, HCl itself is acid, and it has chloride. Later, it comes back as a nucleophile, combining together with the property, the carbocation. But if you combine like this, Ki, here the K is not good electrophile. H was a good electrophile to be attached. But if you add acid separately, okay, this is kind of an acid and I minus the source together, similar to this. So if you give this to this molecule, now this electron is searching which one is more electropositive. Here, among these, most electropositive one is proton, generated from phosphoric acid. Okay? Proton is added here first, forming carbocation. And I minus attack and generated this product. Okay? This one, by chance, this one has a combined two effects. Acid source and chloride source. It can be added separately like this. So that means if you add acid to the alkene, it forms carbocation. So previously we have seen trans-cis equilibrium by acid catalyst. Means by adding acid, it forms carbocation intermediate, and it forms transcend the cis equilibrium back and forth. Okay? Acid and which one is the nucleophile? That's the key point. I minus can come back. If you combine a little different way with the water, no I source, water and another acid, sulfuric acid. So the strong acid we have learned so far is chloric acid, phosphoric acid, sulfuric acid. They are strong acids. And acid and water, there is no good nucleophile there, like a halide. Then even water can come in and attack here, and OH can be added. So chemical reaction is always competing among those species, which one is stronger for the reactivity. Okay? Only one reaction we learned, but there is some variations. Alkene, double bond, electron rich. It wants to give electron to electrophile. If there's any acid, those acids can be good electrophile. First reaction is by giving that pi electron to proton, and it forms carbocation as an intermediate. And it looks for nucleophiles. In this case, chloride. Second case, iodide. Third case, it was water. Water is added and the one proton is removed, and then the product is OH group, hydroxy group is added. Okay? This is how we look at the chemical reactions. Who has highest electron? In this case, double bond, pi electrons. First donation to the H plus proton, forming carbocation, and look for second pattern. Now here, to draw the reaction, okay, this is a common way we draw. Reagent 1, reagent 2, and arrow and product. And on top, usually we put solvent and conditions. Condition may be temperature, or if it's activation energy you give. What kind of activation energy have you seen so far? Heating. What else? Like, how do you write? How do you write? This is light. Quantum mechanically, nu is the light. Other energy? Microwave. Other energy? Ultrasound. This is the common way we use. There's another energy, like a mechanical energy, breaking the crystal structure, and there's some candy. If you break it, then there's some light coming up. What do you call the kind of candy? Huh? There was some candy. It has in crystal. There's a high energy inside. If you break it, then there's a light. It is sparkling, like a sparkling candy or something. That kind of energy is another energy source. People think mechanical energy. Okay. Anyway, this is kind of a conditions. You may put those conditions in here, or it can be a little modified in this way. Now, in this case, the main carbon source is this one. We are learning organic chemistry now, so this is the starting material. This is the product. All others is kind of a reagent. Even though HCl has been used as reagent, but this one is kind of a small extra reactant or reagent. Then, in this case, we have the reagent on top of here. It's a less important the material than starting material. Starting material product is organic molecule. This is not organic. So, reagent on top here, and then solvent and condition on the bottom. This is another way. So this way or this way is a common way how you draw chemical the reaction schemes. There's no fixed rule, but this is kind of general or common way to describe. If you write this reaction this way, then they may see that you have some idea on chemical reactions. Okay. Okay, moving to the next one. This is the next week, the next class topic. Here, let's see small taste. Now, if you do this reaction, this is one product. It may have another product, right? What can be another product? If it forms carbocation, carbocation forms here or here. Right? Now, so far we have drawn intentionally only one product. It has a chance this chloride could go in here or here. But we draw only one product. Same way here, this I could go here or here. But we draw only one. Here, OH could go in here or here, right? But we gave only one. And there is a selectivity. That selectivity was discovered by this person, sounds like a Russian, the chemist name, Markovnikov, found this rule, and the substituents goes in to more substituted position than open position. That's what he found. And that's the selectivity issue which we are going to study later. Okay? So today up to here, any question for these reactions and the reaction mechanisms? 시간이 조금 더 있는데 조금 더 해볼까? 아니면 목요일 날 할까? Okay, up to here today. So you guys start the study from today. The exam is the next Tuesday. You know that, right? Just 1 week away. It's better to repeat maybe the study 3 times. If you study only 1 time through, looks like you understand that, but if you think last part and the first part, you already started to confuse. You didn't learn the chemistry, the reaction much, so this time it's much better, but the final exam, you will learn a lot more reactions. Only condition I give you is just giving you this and this, and what can be the product. Then you need to know Markovnikov rule, and what can be the first reactant with this, kind of many things you should think at the same time. Okay? That's why I'm trying to train you guys, in a sense, which one has a higher electron than the other, kind of rather than just memorizing each case, the general view, then you have a better chance, okay, this is electron rich, and which one can be electron poor kind of approach. Okay? So start right away. Maybe 3 times you review everything, then most likely you will be okay. Okay? 아직 많이 배우기 전에 공부 바로 시작해서 중간고사를 잘 넘긴 다음 본격적으로 반응을 배울 수 있게 준비를 하시도록 하면 좋겠습니다. Okay? Then see you on Thursday.